Okay, and I will also record it on the computer. Okay, so thank you everybody for coming to this second IPARCOS astro-seminar. Today it is a pleasure to have here Professor Avishai Dekel from the University of Jerusalem, Hebrew University of Jerusalem. Well, probably most of you already know him, so I will make a very short introduction just for the students that are new on the field, on the astronomy field. Avishai basically worked recognized internationally because he's working in many fields in astrophysics, most of them related with galaxy formation and evolution. He has many theories of how the galaxies form and evolve, how the baryons are accreted inside galaxies, and also he did several analytical models to reproduce what simulations are predicting, and also to try to understand how the galaxy forms and how we can understand the observations, both in high redshift and lower redshift. And today, basically, he will focus in one of the most recent studies he's leading, that is basically the study of how compaction, these events that are usually seen at intermediate and high redshift, how this can have an effect on the central part of the galaxies and on the black holes, and also on the structure of the dark matter inside these regions. So this is the very short introduction. If you want to add something else, Avishai, feel free, and I will let you to start as when you want. You have 45-50 minutes, and then we have the questions.
Okay, so good evening, everybody. I'm going to tell you today about compaction-driven black hole growth, extended rings, and dark matter cores. And I want to point out three different phenomena at high redshift, which apparently are very different, but I'll try to point out that they have a common reason. One of them is the fact that AGN appear typically above the critical mass, 10.5 stellar masses. This is work by Foster Schreiber et al., showing that the fraction of galaxies that host AGN have this very typical scale here, and they appear above this scale. The second very different phenomena is that there are many rings, especially at high redshift. This is one of them, star-forming ring, clumpy ring. And the third is a new result from Genzel et al. Recently, finding that the slope of the density profile at small radii of the dark matter has a core, has a slope close to 0, as opposed to being around 1 and above in other galaxies. About a third of the galaxies, of the massive galaxies, have this low core. And I'll try to argue that all these three phenomena come from the same thing, the same process that almost every galaxy suffers in its history, which I called compaction to a blue nugget. And I'll talk about it in my talk. So I'll tell you about compaction at the golden mass of galaxies, and then black hole growth, ring formation, and cores in massive galaxies. So at compaction, there are several papers in the last several years that we were working on at the golden mass. This is the golden mass as a function of halo mass. If you look at the efficiency of galaxy formation, you see a peak at about 10 to the 12 solar masses of the halo. There's low mass quenching and high mass quenching, which suppress the star formation in those two regimes. What is the origin of this? Also, the fact that black holes usually appear above the golden mass in this regime. So, if you look at redshift, going from right to left, and the halo mass, There's a typical halos, the pressure sector mass that formed at different time, rising very steeply. The first mass scale is the supernova feedback, around 100 kilometers per second, below which it can be effective. Above this mass, it is ineffective simply because of some energetic arguments. You take the supernova energy into the ISM, the binding energy of the gas, and you get this critical mass as derived long time ago. A second scale is the shock heating scale of the halo, slightly below 10 to the 12 solar mass at different times. You have hot CGM above and cold CGM below. And actually, you can have cold streams in this regime, not so relevant for us today. So if you put together those scales, you find out that between redshift 2 and below, they coincide, all those scales. And this is what drives this golden mass, okay? This is what makes galaxy formation most efficient in this regime. I'm going to talk about using simulations, mostly the ones that we did with Daniel Severino, the Vela simulations. I've listed here are many collaborators. These are the 3 Spanish ones. This is a very high resolution cosmological suite of simulations, 25 parsecs in the disks, one of the highest cosmological simulations that we have around. And this is really illustrating this phenomenon of compaction to blue nugget. From left to right, you see the gas flowing in, compactifying and giving us a blue nugget, a very dense star-forming 1 kpc region, after which there is central depletion of the gas and eventually formation of a ring. While those stars that compactified here make this very nice red nugget at the center of the galaxy of stars. This is the stars. So this is the main phenomenon we talk about, and you see it very nicely in this simulation. If I'm looking at the mass as a function of time within the inner 1 kpc, first the gas, this is the compaction in the gas. Suddenly there's a rise and compactification by a factor of more than 10 in the density, and then depletion of the gas from there on. This is the compaction time, and the star formation rate, just if you follow the Koenig-Schmidt relation, follows with a similar peak at the blue nugget phase. The stars that were built here, now because there is quenching after the peak of the blue nugget, remain pretty much a constant stellar mass. That's all within 1 kpc. Observationally, this is one way to see it, and it's been observed. If you look at the central density of stars and specific star formation rate, these are 8 galaxies here, you see the evolution from a diffuse phase, this is the compaction, to a blue nugget, and then quenching at the blue nugget phase, simply because there is supernova feedback induced by the compaction, and then it stops the star formation and depletes the gas from the center. And this is the observational counterpart in Barrow et al. And several other papers, very similar behavior. Of course, here you don't know what the evolution is like, but from the simulation we learn that this is the kind of evolution, compaction to a blue nugget and then quenching. So this is seen observationally. The blue nuggets are actually seen observationally at high redshifts. Now, you may ask, what is the trigger for compaction? I will not go through all the ideas that we have, but the main reason for compaction is mergers in which you lose angular momentum. As long as you lose angular momentum, you can have the gas compactified to the middle. And matter is the main driver. About 50% of the galaxies that go through compaction are because of mergers. But there are other ideas of flows, counter-rotating, and so on. The most important part, coming from several works, in particular deep learning analysis with Mark Werder's company, is the fact that there's a magic mass for blue nuggets for the compaction, around 10 to the 10 solar mass, the same golden mass I was addressing before. So the compaction, that's the most important thing to realize, usually happens at the golden mass. And that's very important for what the implications will be. So please remember that compactions occur in most galaxies when, at whatever time, they reach this magic mass as they grow from bottom up. Supernova feedback suppresses the compactors below the golden mass, and the hot CGM plus AGN feedback suppress star formation above it, but maximum efficiency is in this golden mass. Now, this compaction makes many transitions in the galaxy properties. And again, I will not go through all of them, star forming to quench, diffuse to compact, etc., etc. Most important, I'm going to address the three phenomena we were talking about. One thing I will mention is the fact that the dark matter dominates the inner parts of the galaxy before the compaction, but because the gas was brought in at the compaction, the dark matter becomes subdominant and the baryons dominant the center later. This is the bulge dominant galaxy of today, and this will be important for what I'm going to say later. Also, I'm going to show you that the black hole growth occurs at this mass. And this is the magic mass we are talking about. So let's talk about the black hole growth. How the compaction connects to black hole growth. There's a paper now submitted very recently on this. This is a few years ago, Johan Dubois made same simulation with supernova and without supernova, but with black holes. As you can see, as a function of time, the black hole mass goes very quickly if there is no supernova. But when you put in supernovae, there is suppression. Supernova feedback suppresses the growth of black holes at low masses. And then there is a growth. However, there is a measure here which triggers this growth. And you can see this measure, this galaxy, coming in and hitting this galaxy. And you see the effective radius goes down at this point. This is the compaction event that triggers this growth. So below the golden mass, there's a strong supernova feedback, which suppresses black hole growth. And then the compaction overcomes it, and there's rapid black hole growth soon after, plus AGN feedback eventually. These are new simulations, a new horizon, also by Dubois et al. Results from another paper that, the paper that is now have been submitted. And this is one of the galaxies. And what you can see is, this is expansion factor. This is time going from left to right. You see a compaction event in the gas within 1 kpc. And following this, you see a black hole growth, which is the black. The black is the black hole growth, except that it's multiplied by 4 orders of magnitude to put it in the same figure. And you see this follows the compaction. What you can also see is that at this time of compaction, the potential well becomes much deeper. That's the gravity potential well at the center. And you can also see that the radius of the black hole suddenly goes down. The black hole was wandering at about 1 kpc around the center of the galaxy, but the compaction event locked it into a small radius at the center. And that's a key feature for the growth of the black hole, because near the center it can really accrete faster. So what you can see here is the correlation of the different parameters of the black hole growth and the compaction event of the galaxy. This is the time for the onset of compaction. This is the time of the peak of the blue nugget. This is how the potential well changes. This is the time of the biggest change of the deepening of the potential well. And this is the time for the lockdown of the black hole to the center. And you see they are all, these are 8 galaxies here simulated in this cosmological simulation. They are all pretty tightly correlated. In pictures, you can see, again, this is the compaction, this is the blue nugget event. You see the black hole in black dot wandering around at large distances. But when the compaction occurs, the black hole is now locked to the center, as you can see here. Because the potential well became deeper, and because there's drag force by the gas that was brought to the middle. So now the black hole is really start to grow as the compaction drives it in. And this is how you get black hole mass versus stellar mass in these 8 galaxies. You predict, we predict that they will lie below the usual linear relation if you are at 10 to the 5 solar masses, small black holes. For each galaxy, I've marked here the blue nugget place, and you see they all occur roughly where the transition is. This is not unique to our simulations. You see a similar thing in Eagle and in Fire in 2 different simulations, always at the same golden mass or magic mass. So this is a robust feature. We just showed very clearly that it's all correlated with the compaction event at this mass. So this is a story. Below the golden mass, there's a supernova phase where the growth is suppressed. Above it, there's the hot CGM phase and AGN feedback, which suppress. But at the golden mass, there's a compaction event which triggers this growth. And observationally, this is a paper we did with candles. We plot the compactness again as a function of star formation rate now going down. And what you see here is the compaction and blue nugget. What's plotted here in color is again the frequency of the galaxies hosting an active AGN. And you see that the peak is at the blue nugget phase, not after quenching and not before. And that's exactly what these simulations predict. So the compaction triggers the black hole growth and the AGN quenching. This is what I showed you in the first slide by Foster Schreiber et al. Many galaxies, redshift 2, and you see this typical behavior, and we can reproduce it in this model. We compute for several galaxies the black hole luminosity and stellar mass, and then we cut for the active AGNs, and we get this line. You see the blue line is quite similar to the observed line, which is the red. At the magic mass, there is this growth. So that's the story of the black hole growth. Let me move on to the disks and ring formation above the golden mass. This is a paper published recently. 2 papers. First, if you look at this diagram of redshift and halo mass, and you ask, where do we find disks? For example, in terms of rotation over dispersion velocity. Let's say 3 is going to be our magic distinguishing number. You find that disks occur above halo mass of 10 to the 11 or 2 times 10 to the 11. This is the blue. And if you look below, your galaxies are dispersion dominated. They are red or yellow. So there's a magic mass which tells you at all redshifts where you can find disk and where you don't expect to find disk. What is the reason of this? Well, it's a very simple reason. This is the same diagram, but now the color is the angle between the spin of the galaxy in 2 successive times, about 1 orbital time between the 2 times. What you see is that in the region where you have disks, the color is blue. The angle is very small. The spin is stable. But if you look below the magic line, at low mass galaxies, the spin flips in every dynamical time. Namely, the frequency of mergers that cause these flips, the time scale between merger is less than an orbital time of the disk. And that's why the disks are being destroyed. It turns out, surprisingly, this is pretty much a threshold of mass, not in redshift, or even at high redshifts. If you are massive enough, we predict, the simulations predict you will get disks. And this is now, there are hints that this is happening, even at redshift 6 or 7. Okay, but I want to talk about rings. So how do you build up a ring? Those streams that build up the galaxy, this is the real radius of a galaxy, this is the gas in one galaxy. And you see it comes in with a lot of angular momentum. This is the impact parameter. And then there are torques and friction, which brings the gas in and builds a ring. That's understood by torques, tidal torques on large scales. And that's all explained in nanovigital. However, how do you keep the ring for a long time, as we see in the simulations? You must retain the angular momentum, and that's the key. That's where compaction will come in a second. So back to the same picture I showed you, you see very nicely that after the compaction, there is a ring formation. These are 5 different galaxies, just to show you that this is a robust feature in many galaxies. At redshift 5 or 3 or 2, you get those nice rings. Star-forming rings, pretty empty of gas and star formation, but with a massive bulge in the middle. Why is it long-lived? Little simple toy model theory. There are 3 time scales involved. There's the accretion by streams that generate the rings. There's angular momentum transport outside that make the ring shrink inside by instability. And you really want for the ring to survive for a long time that the accretion time be shorter than the transport time. Otherwise, the ring will disappear before it's being built. Second time scale is the time to depletion of the gas and star formation, quenching of star formation. To get a ring and not a full disk, you want the depletion time to be shorter than the transport time. So you really need a long transport time in order to see a ring for those 2 reasons. Well, some years ago, I and others thought that the transport time is quite quick. It's about 1 or a few orbital times. There's one key parameter that comes in if you do the calculation, when you do valence disk instability calculation, and that's the ratio of the mass in the disk over the total mass encompassed, including dark matter and stars and so on. This is the key parameter, remember it, except that if this was true, then the ring would not have survived. Too fast transport that destroys the ring. But what we did recently is we computed the torques exerted by a spiral ramp structure on a ring around this. In some approximation, simple approximation, and that's the result. That depending on this parameter here, if it is low enough, say below 1/3, then there's a strong dependence on this parameter, which makes the transport path, time much, much longer than we thought it is. Not a few orbital times, but many orbital times. So the transport is slow to keep the ring going if delta D is small. If there is, and how do you make delta D too small? For example, if you get the total mass much, much higher. For example, by a big, massive bulge in the middle of the galaxy that was generated by compaction. A compaction generates a high mtot compared to a gas disk, and this generates very slow transport inwards, which is long life for the ring. So when the rings survive, let's estimate the timescale very crudely. The orbital time of a typical galaxy at a given redshift is this. The accretion time is given by this. The transport time, which we just computed, is given by this. And the star formation rate is sometimes, many times the threefold time, all in terms of the orbital time now. So now I can compare them to see when I'm going to get a ring. Remember, I want the ring to accumulate, so the accretion to be faster than the transport. And you find by comparing those two, delta T is less than 0.2 as a function, and it depends on redshift in a very weak way. And if you want the depletion, the star formation rate to be shorter than the transport time, you compare those two, and you also get delta T less than 0.3. So in general, you can argue very simply that once delta T is below 0.3, once there is enough mass in the middle, then you get strong rings that are long-lived. So again, the compaction is the reason for the ring formation. In fact, once you get a ring, this time scale become even longer. One can show that. Now, to show you how robust these rings are, these are pictures from the TNG simulations, which have AGN. Our worry was maybe AGN feedback in these massive galaxies above the golden mass will destroy the rings. Well, they don't. Very nice rings show up in the TNG simulation with AGN. This is an old paper by Elmegren. Different galaxies, redshift 1 and above, nice star-forming rings around massive bulges. This is a very well-known phenomenon. These are 4 galaxies round simulations, but observed to show what they will look like in HST. And indeed, these are 4 different galaxies from HST, ongoing work with Javalisco and his student, where we see cold star-forming gas rings around massive red-ended bulges. Very similar to the predictions, and we make some quantitative comparisons. In fact, you don't have to go to high redshifts. Samir Salim showed 10 years ago that most galaxies in the Green Valley actually are ring galaxies. Very similar to the high redshift galaxies we just saw. And you don't have to go very far. This is the famous Hawk galaxy, I think the first famous ring at low redshift. You all know the Sombrero, and you all know M31. They all have gas rings start forming. The question is the mechanism for ring formation the same at low redshift and at high redshift? And I'm going to address three mechanisms. One is the bullseye collision. A big galaxy goes through the middle of another galaxy, generates a shock wave that propagates out. These are the observable predictions, and in particular, it predicts outward shock velocity, and it tends to occur in low mass galaxies where I showed you the mergers are very frequent. We'll go back to these predictions. This is one mechanism that people address that can make rings. Another mechanism is in secular disks, there are rings that can live in one of those resonances, in the inner link belt resonance, in the outer link belt resonance, or in the co-rotation resonance, defined by the pattern speed compared to the actual rotation speed. Now, the one thing, there was a lot of work about rings this way, but the one prediction that this theory gives is that there's outflow away from the co-rotation radius. So you expect outflows either interior to the ring if the ring is here, or exterior to the ring if the ring is here. Also, sometimes it has to come with a bar, a lot of stars, and the galaxy have to be secular, very nice disk, not like what we have at high redshift. At high redshift, in our simulation, we can actually rule out these secular evolution resonances, because what I plot here as a function of radius in full galaxies in red, the radial velocity. So if it's below 0, it's a flow inwards, as you can see in the purple arrows. So we always have flow inwards, not flow outwards, as this predicts. So in those high redshift, you can really rule out the secular evolution resonances as the mechanism. Maybe in this one case, there is some outgoing ring, positive red, which may indicate a collision. So for the observers among you, these are the different predictions for the three different scenarios: the resonance scenario, the collision scenario, and the stream-fed scenario I discussed in our simulations. In particular, the collision is expected at low masses, the stream feeding at high masses. This can happen at all redshift. This is typically at high redshift. Resonance is typically at low redshift. The inward velocity I talked about, while these ones predict only outward velocities. And the central body, the key to stability of our rings at high redshift, is having a massive bulge. And there are many more details here which I will not go through. So there are three scenarios, and maybe at low redshift it's more this kind of scenario. At low masses it may be collisions, but massive galaxies high redshift are probably stream fed, and they are driven by the compaction event. And finally, I'm going to discuss with you ongoing work about a new phenomena, which is very surprising. The observation is in Genzel et al. And this is the paper we are now working on, not yet finished. So what's the story here? I will not go into the details of observations shown in one slide. And that's in Genzel et al., actually 21. 41 massive disks at redshift 1 to 2, just above the golden mass. And what is found is that about a third of these galaxies have a dark matter core. So if I write the inner slope of the density profile of the dark matter with an index alpha, NFW typically is 1. This is half the galaxies or most of the galaxies, but 1/3 of the galaxies tend to have alpha close to 0, namely their cores. Also, in these galaxies, what you see here is the dark matter fraction within the effective radius. It's low, which is consistent with this dark matter cores. Now, why is this so surprising? It's surprising because supernova feedback, which we usually blame for cores in low mass galaxies, in dwarfs, is supposed to be ineffective above the golden mass by simple energetics that I told you in the first slides. Also, all the simulations that I know, every one of the cosmological simulations fails to reproduce a massive core, which is as massive as about 10 kpc in those massive galaxies. So how come the observations give you a core? Well, there's a lot of assumptions here in the interpretation. So one by saying maybe the interpretation of the observation is premature, maybe. But if it's true, it's very exciting theoretically. So our idea is a hybrid scenario for core formation, which is made of two processes: dynamical friction heating by satellites. As they go in, they suffer dynamical friction and they heat up the dark matter in the middle. And then AGN outflows that help creating this core. So first, dynamical friction, which by the way was mentioned earlier as something to generate cores, but it didn't work in massive galaxies for 10 kpc. You have a satellite suffering dynamical friction, so it shrinks to the middle, and also tidal stripping. The tidal stripping, well, first, the dynamical friction is stronger if the satellite is more massive. Second, that's the key, the more compact the satellite is to begin with at the real radius, the less it's going to lose by tidal stripping. And then it will penetrate to the inner cusp of the big halo with a higher mass and cause dynamical heating. So the compactness is the key. Then, once you heat at the center of the dark matter by this dynamical friction, AGN outflow will cause stronger expansion of the dark matter into a flat core. And I'm going to address those two in the few minutes that are left to this. So this is just supposed to be a movie that doesn't work for some reason. So I'll go directly to the toy model to understand how dynamical friction heating works and how it depends on the compaction. So in my toy model, I'm going to assume very basic and crude stuff. This is how the tidal radius of the satellite is defined when the satellite is at a radius r in the host halo. What you have here is the slope density profile of the host halo and the circularity of the orbit of the satellite which acts to push the satellite outer shells outwards by centrifugal force of the orbit and helps the disruption. So that's a classical definition of the tidal radius of satellite. Now we use a new profile, and if you remember the talk by Jonathan Freundlich last week, whenever it was, we have this profile which is a very flexible inner slope, alpha. It can describe a cusp, alpha of 1, or a core, alpha of 0, and it's analytic. It has many expressions. So the satellite is described by this. There are two parameters here, alpha, the slope, and concentration. So this is a two-parameter profile that can do NFW cusp or a core in a very general way. If I combine those two assumptions, I end up with the fraction of the mass once the satellite is at a radius r in the host halo. This is the mass that's left. I call it F. It's a function of the host halo profile, the eccentricity of the orbit, and most important, the compactness of the satellite. Now I put in dynamical friction, which is proportional to the mass of the satellite squared. I look at the work done by dynamical friction inside the core radius, and I get the total energy deposited by dynamical friction relative to the energy, kinetic energy in the core. It's proportional to m squared, and it's going to be for a unity, namely significant, if the fraction of the satellite that comes in is about 20%. If it's less, you're not going to heat up the core. Now, if you have cosmological satellites, then you can assume the accretion rate and what's the typical satellite mass in the massive satellites for a given halo mass. And this is our final result, that you can have of order unity heating of the energy in the cusp if your satellite is of 20% mass when it comes in, if the redshift is high enough, and if the time that the system is hot and available and remains hot is of order unity. And so cusp heating is F is above 0.2. And for this, you really need a compact, massive satellite. And you have to be at high Z, and you have to know that tau is not much smaller than unity. Now, if you look at simulations, you find a very interesting feature. You see that the profile, the mass profile, as a function of radius, has two universal shapes. If you are before the compaction, below the golden mass, then you have this diffuse profile in different times. This is redshift. Each one is different redshift. You go from high redshift to low redshift. And then the compaction occurred, that's the dashed line, and you end up with a compact satellite. And these are the Dekel-Zhao parameters, concentration and slope, that characterize this compact satellite above the magic mass and diffuse satellite below the magic mass. So you expect dynamical friction heating if you are compact, namely if you are post-compaction and if the satellite is above 10 to the 11 solar mass. This is why the host galaxy has to be above 10 to the 12 solar masses to end up with the core. If you are a smaller halo, you don't have satellites that are as massive to be compact. They're going to be diffuse. So This result is shown here as a function of concentration and slope. These are the parameters. This is the mass that remains, and this is the compact satellites. This is the diffuse satellites in two limiting cases, where the orbit is radial or where in tangential. And the truth must be somewhere in between. So if I read the number for the compact, I land at about 20% as needed is really coming into the core if you have a compact satellite. But if you have a diffuse satellite, much less is coming in. It's not going to be effective. And the same thing about the energy deposited in the core. For the compact satellites, you get for a unity significant heating if you use the compact post-compaction satellites above 10 to the 11th solar mass. But if your galaxy is below 10 or 12 solar mass, satellites are below 10 to 11, you don't heat up very much. So we do nice semi-analytic simulations. Santi, I'll take another 5 minutes, okay? This is a SatGen, a nice semi-analytic simulations. You see the orbit. This is the compact satellite. It goes to the center in the first pericenter, second pericenter. And the diffuse satellite actually hang around to the third pericenter to come in. As a result, the fraction of mass for the compact satellite is 0.3 at the core radius, but for the diffuse satellite is below unity, below 0.1. And energy is very similar to what the toy model predicted. Above unity for the compact, well below unity at the cusp radius for the diffuse satellite. If we take a cosmological sample of satellites coming in one after another using the cosmological mass function of satellites, a very similar result. You see that at the core radius, if you are massive halo, which has compact satellites post-compaction, you heat up the core by a factor of 2. But not if your halo is below the magic mass. And it doesn't have compact satellites. The last point I want to show you is that if you do n-body simulations, which are really one n-body satellite merging into an n-body halo, we find that soon after the first or second pericenter, dynamical friction heating makes the kinetic energy goes up compared to its initial value at the core radius. That's the heating. However, there's a worrying thing. If you wait a while, there's a cooling. The reason is that the hot cusp is now expanding to reach a new Jeans equilibrium, and it's cooling back down. So being hot is a temporary thing. It's only a fraction of the real time, but it's a long fraction of the real time. And that's very important. So let me show you now the last thing, the response to the outflow. Again, I remind you what Jonathan Freundlich say about supernova feedback, but now I apply the same theory, the same model to AGN feedback. What we assume is that you have kinetic profile and potential energy profile and density profile in Jeans equilibrium, and then we suddenly remove a big fraction of this gas from the inside out. The gas is removed, the potential will become more shallow. Nothing happened at the very instant of the removal to the kinetic energy or the density profile. But if you wait a while, there's a relaxation, we assume energy conservation, and now the kinetic energy goes down and the potential keeps going, and you end up with a core. That's how outflow generates a core. Now the heating is the key. And this is my last result. So this is density profile of the dark yellow as a function of radius in 3 different cases. If I just take an NFW profile and make an outflow by AGN, this is the kind of flattening that I get. Moderate, little flattening. However, if I have a heated gas by dynamical friction, you start with the same NFW, but the dark matter is kinetically hot. The particles are close to the escape. Now I have the explosion of the AGN. I have very strong flattening to a 10 kpc core. Exactly what I wanted by those 2 processes. If I wait enough time and there is cooling to a new Newton's equilibrium, then I do have some flattening, but then the expansion is not as strong as it was for the strong heating. So the heated gas by dynamic friction is more responsive to outflows. Now look at the numbers again. This was my estimate. And I said that heating will be good as long as tau is a long time. Now from the simulation, we found about half of the real time, which makes this still around 1. So the conclusion is that when you have a cosmological sample of satellites coming in, the cusp is maintained hot for a long time. If you're massive enough to have the compact, this is for compact satellites, for the massive satellites. And then you'll have a nice core formation. So what you need is cosmological simulation which can resolve these satellites. And let me summarize my conclusions. There's a golden mass. There is wet compaction to blue nugget at the golden mass. Black hole growth is triggered by a compaction event near the golden mass. Rings form above the golden mass because of the formation of a massive bulge. And dark matter cores in massive galaxies, if they're above the golden mass, okay, can be formed by a 2-stage process, dynamical friction heating, if you're massive enough and compact enough, and then the response to this hot dark matter to expulsion of gas by AGN feedback. Thank you very much.
Great. Thank you a lot, Avishai, for this very, very nice talk with so many very interesting results. I have many, many questions, but I will start with the people that is in the talk to ask the first questions. People, feel free if you want to unmute yourself and start asking questions to Avishai. Gary, please proceed.
Gary, you're mute. You're mute.
Yeah.
Avishai, I'm overwhelmed with all this information. This is terrific work. But I don't understand why you don't see in the hydro simulations that you can get this issue, right? That you can see this transition of a cusp to core in the massive galaxies, because the simulations that you mentioned, Vela, and also Nihao, and also New Horizon, and also Illustris TNG 100 and now 50, have quite good resolution. So
Yes.
Is that they're missing physics?
No, it's the resolution, first of all. You need satellites which are above 10 to the 11 solar mass to be resolved. Now, none of the simulations that you mentioned, including Vela, resolve the satellite this way. We resolve the host halos of 10 to the 12 solar mass, but we don't have above 10 to the 12 solar mass halos, which will have the satellite resolved. So what you need to do is a higher resolution simulation in more massive halos, such that not only the disks in those halos will be resolved, but also the satellite that come in that are 10 times less massive will be resolved. Also, you need more than 10 million particles in those satellites. Otherwise, there's artificial displacement as they go in. So none of the simulations that exist have the proper resolution. However, it's not unfeasible. You need to go only one step up in the resolution and the masses, and you end up doing this. Second thing is, you may need to boost up the agent feedback. And a very easy way to do this is by clumpy accretion. And this is, again, something Johan Dubois and others are trying to do now with us to try to see if you can boost up the agent feedback to have a stronger effect of response. Because the feedback we have today in any of the simulations is not strong enough. Maybe just the resolution here will help to get the satellites compact enough and resolve enough.
Okay, thank you.
Hello, Avishai. This is Rafael. Avishai, it's really good to see you. And sorry that I was not able to say hello before because I could not unmute my micro. So thanks for an excellent talk. As always, lots of information. I just have one quick question regarding the first part of your talk. When you showed the evolution in the stellar mass and the gas mass, the dark matter, and also the black hole, in the very central region of the galaxy. And you showed us that during compaction, the stellar mass increases very, very rapidly and then takes over dark matter and becomes baryon dominating in the center. Exactly, that is the one. I think if you put the black hole evolution, so the black hole actually keeps increasing beyond compaction, right?
Yes,
so
it's increasing, and this is just schematic. It really goes down, up like this and keep increasing.
It keeps increasing. Yes. So what is feeding the growth of the black hole beyond compaction?
Well, it can be more accretion. It can be mergers of black holes and from other galaxies. But as you can see, the peak growth rate is here.
Yes.
And this is a slower growth, significantly slower growth. Now, this is on a schematic. I should have shown you, maybe I can show you.
I think you had another one actually with more.
Yeah, I can show you some examples. I can show you a real example from a real galaxy.
Yes, exactly. And you can see that it grows quite a lot. Actually,
there's a very strong growth here.
Yep.
And then a slower growth.
Yep.
Until it really stalls. So again, this can be galaxy mergers. And maybe, these are very small scale processes. Remember, we're talking here about something that happened on much, much smaller scales. So it really, maybe it takes time for the gas to really accrete, to lose angular momentum. It's the inner parsec problem that may take some while before it really goes to the black hole.
I see. Okay, thank you, Avishai.
Yeah, can I ask a question?
Yeah, please.
Hi, Avishai. Thanks very much for the talk. I really appreciate it. Learned a lot from your compact series of results, as usual. I had a question on the formation of the cores by accretion of massive satellites, and certainly the role of the density is the density of the satellite is the important one.
Yes.
The question is then, would you predict that the baryons at the core afterwards are dominated by accreted baryons? And if so, would then perhaps be a signature in the metallicity of the bulges of these cores with flat density cores? So they have lower metallicities?
That's actually a good point. I was talking here only the dark matter halos of the satellites coming in, etc. One has to do it properly with simulation, with the baryons. And I'm not in a position to tell you, but you have to worry about the fact that you need the baryons to remain in stellar bulge, for example, while the dark matter is expanding. And this is something you have to worry when you do it properly with the baryons. We have not done it yet. And again, this is a challenge. As Gary said, we'll have to do it with good simulations. And this is a challenge for future work. But you have to worry about them, about metallicities and galaxy properties. We worried about this in the context of the blue nuggets. And we do in our paper on blue nuggets, the ones we publish and the ones that are coming, there is discussion of metallicity and so on in the blue nuggets. But in the context of the response of the halo to dynamical friction and to agent feedback, we have not done it yet. So I think it's a very good question to be done.
Good, thanks. Thanks very much.
So, more questions? I have one related with the massive cores. That is, in the Genzel observations, that you have shown that they observe this kind of very dense cores, very massive cores. My question is, this cores, this can depend on the environment of the galaxy. This should depend, no, on the environment of the galaxy that has this compact inner part. Because basically, if you are suggesting that these cores are generated by the dynamical friction of the very big satellites, this probably will happen more times in dense environments than in less dense environments.
So these galaxies were selected mostly in the field. They are not cluster galaxies. They are all SFGs. They are big, massive disks. So there's no big difference in the environment. What may be different is if you just happen to have a satellite that's more massive in one galaxy, or a satellite that is a more radial orbit, this will be more effective. Or it has a bigger black hole that explodes with AGN, that's more effective. So this is the kind of, all this scatter in all those properties. The compaction of satellites have a scatter, the circularity of the orbit, the initial dark matter halos, cusps, these all have scatter. So it's the third tail which give you enough. And as you saw, everything is marginal. We eat it up, but not by a big factor, maybe by a factor of 2. So it's quite easy to think of a galaxy where this did not work. And some galaxies where this worked very well, just by this scattering of things.
Okay, thank you. Somebody else has also some questions.
I want to mention that Omri Ginsburg, who is here as in the audience, is one of the main partners in the study of disks and rings that I mentioned in the middle of my talk. Even though he has a picture of a collision-made ring, we don't believe this is the way most rings are formed. Yes, sorry.
It's Armando.
Yeah,
Armando,
well, I can repeat it. I mean, thank you, Professor Dekel, by the talk. It was really nice. I learned a lot. I have just one quick question. It's regarding the first part of your talk. You said that apparently roughly 50% of the I mean, in the 50% of the cases of this blue nugget formation, there are some mergers involved. So you also saw the result of a simulation of the position of the black hole of the massive host, I assume. So my question was, what is the fate, let's say, and also the time scale for the other black hole of the merging system? Whether it can play a role, it can actually get together with the other one, both in the center, which will also, of course, boost the growth of both.
Yes, some of the black hole growth has to do with mergers. Actually, I would think that this growth of the stellar mass indicates a growth by merger. So the black hole comes in and it joins this black hole, but the black hole growth is mostly by accretion of new gas. It's not by just joining black holes. You grow by joining black holes, but that's not the major growth factor. The major growth factor is by new gas accreted or stars accreted onto the black hole. That's what turns out in those simulations.
But I would think that the process will help also to drive the two black holes together. This high concentration.
The friction with, yes. And both the potential well, remember, there's a potential well here that becomes deeper, and it brings the black hole to the center, and if there's a second black hole, it's doing the same thing. Okay. So the compaction does bring the black hole together, may help you solve the need for angular momentum loss that brings the black holes together.
Okay, thank you very much.
Okay.
Okay.
Yeah.
I have a question. I mean, very nice, very inspiring talk, Dekel. This is Jorge Sanchez Almeida. This is about the mechanism to produce cores in massive galaxies. They require, if I understood you correctly, of the accretion of a massive compact satellite. And I wonder whether the residual of these satellites should be seen in the core. So from an observational point of view, I would expect that galaxies, massive galaxies with cores, do show compact stellar clusters. Do you know whether that thing has been studied? To what extent this makes sense?
Well, observationally, we do see in galaxies after above a given mass, normally a red nugget in the middle of the galaxy. That's well known that the centers of massive galaxies, today's ellipticals, have compact. Now, it's not it's not a small stellar cluster around a black hole like in the Milky Way. It's a 1 kpc red nugget, so it's a big.
But this is the kind of satellite that you expect to heat up the?
No.
And produce the core?
No, sorry. In the satellite has a compact, another 1 kpc compact red nugget or blue nugget in the middle that comes in and joins the more massive galaxy core.
Yeah, but these satellites should be, I mean, the courses of these satellites should be around when you also observe the core. So somehow I would expect to see, in addition to the center.
They get dispersed eventually, even if they're compact. At some point they get dispersed. Let me try to show you again the movie that didn't work before. I don't know why it didn't work, but the satellites eventually can totally get disappearing.
So they get blended with the rest of the stars that you have in the core.
As you lose mass, you get totally disrupted. And this particular satellite actually was not compact enough, and it got disappeared even before reaching the very center.
Okay.
So just imagine a satellite a little more compact. It will reach the center, but only with 10% of initial mass. However, this is enough, as we saw, to heat up the core. But you do want some of the baryons to be in the middle here and generate, I will call a red nugget in the middle of the big halo. So yes, the answer to your question is yes. You expect to see them. And I think you see them in most galaxies. Those massive galaxies, if you look at the Gensel results, those massive galaxies typically have a massive central bulge.
Okay,
That's the remnant of many satellites that came in. Okay.
Thank you.
I have another question now regarding the rings. Can you make a prediction of how the radius, the typical radius of these rings, or maybe the thickness of the rings, or if there is a dependence on the time from the last major merger or compaction? Can you make these kind of predictions? Can the rings be used as a proxy, for example, for the last major merger or the compaction?
It's a good question. A very good question. As you can see from here, initially, you don't have a ring, you have a disk. And after a while, it develops a ring. And it takes a few dynamical times. This is actually a much later redshift than this was. So initially you make a disk and slowly you evacuate this. And this is the time scale that I was talking about when we discussed the rings. So indeed, the time scales are very important. And, you know, it will take you a while, maybe 5 orbital times before you evacuate this and you get a ring. So in principle, the answer to your question is yes. We have not done that. What we have done is really looking at cases well after the ring is formed and compared, because this is long-lived. So many more rings you will find long after when they're stable. And only the minority of the rings you'll find right after the compaction. But I think you make a good point. This is something we can look at and really quantify this. I think it's a good idea.
Nice, thank you. So if there is some other question from the audience, we can take a couple more of questions. Okay. Well, I think everybody looks satisfied, but no more questions. Thank you a lot, Avishai, again, so we can leave it here. It was a pleasure to have you here, and I hope we can have you again maybe in a future for new works.
Thank you very much. It was a great pleasure to be hosted and to talk to so many nice good people that I know some. Thank you very much.
Thanks. Bye. Have a nice day. Good night. Thank you.
Bye-bye.
Bueno, David, ¿estás por aquí? Quedamos solo tú y yo.